Hi everyone. I want to welcome you to section 7.2, which is going to be about integrating products of trig functions. This technique is important to learn because products of trig functions come up frequently in the analysis of vibrations or signals, and that's a very typical application in engineering, physics, and math problems. So this might seem like a little strange that we're focused in on this really specific family of functions, but they have a lot of application in analyzing anything mathematical that oscillates. This one is a little weird because it's going to consist of a bunch of techniques that are unique to the particular type of functions that you're looking at. And the key tool that we're going to use for most of these is U substitution. We're also going to need some trig identities that I want to remind you of. The big families of trig identities that turn out to be important in calculus, and of course they don't tell you what the important ones are and what they aren't when you're taking trig, if you've taken trig, are these. So there's the identities that are usually called the Pythagorean identities because they're derived from right triangles on the unit circle, and those are sine squared x plus cosine squared x is equal to 1. If I take that equation and I divide everything by sine, I get 1 plus the cotangent squared of x is equal to the cosecant squared of x. And if I take the same equation at the top and I divide everything through by cosine, you get tangent squared x plus 1 is equal to secant squared of x. So these formulas give you ways of moving back and forth between sine squared and cosine squared, between cotangent squared and cosecant squared, and between tan squared and secant squared. The second set of identities we're going to be using are called the half angle identities. And those say that the sine squared of x is equal to 1 minus the cosine of 2x over 2, and that the cosine squared of x is equal to 1 plus the cosine of 2x over 2. So these are ways of reducing the powers of a sine function. And you introduce this additional 2 here in the angle, but when you're dealing with an integration problem, I don't know how to integrate sine squared, but I do know how to integrate something that looks like cosine of anything x. Okay, so these guys are called the half angle identities. Other than that, the basic technique that we're going to be using is U substitution. This video is going to consist mostly of prototypical examples that will show you the technique that applies to a more general case. So the first thing that could happen is we could have products of sines and cosines where either the power of sine is odd or the power of cosine is odd. So the prototypical example we're going to look at here is the integral of the sine squared of x times the cosine of x dx. This is one where we actually have a U substitution available because if I let U be equal to the sine, then du is the cosine. If U is equal to the sine of x, then du is the cosine of x. And this integral turns into the integral of u squared du, which is 1/3 u to the third plus c. And if you substitute back, you get 1/3 sine to the third of x plus c. So this might seem like an easy example of a problem that you might have had in the U substitution section, but the key point here is that this idea of having this extra sign floating around to be the du turns out to apply anytime you have an odd power of sine, because all the other signs you could turn into cosines using the Pythagorean identity. So let me show you a more complicated version of the same problem. If instead you had the integral of sine to the third of x times the cosine squared of x dx, again, the important thing to identify here is that the power of sine is odd. And that means there's an extra one. So I can rewrite this as sine squared of x, cosine squared of x, sine x dx. So I've just popped one of the sines out and stuck it over with the dx because that's going to be the du that we get when we use substitution. I'd really like u to be equal to cosine. The problem is I've got that sine squared floating around in there. The answer to getting rid of the sine squared is to use the Pythagorean identity that says that sine squared of x is equal to 1 minus the cosine squared of x. That's like substituting out the sine squared and putting in something that's going to be a u. So this is the integral of 1 minus the cosine squared of x times the cosine squared of x times the sine of x dx, where again, I'm putting parentheses around this to emphasize I have preserved that extra copy of sine to be the du when I do the u substitution. So let's do it. Let u be equal to the cosine of x, and du is equal to minus the sine of x dx. And that means that minus du is equal to the sine of x dx. Well, there you go. I have one of those saved up right here. So popping that extra power of sine out gave me something that the du can become. And after you do the substitution, what you're going to get is, well, the negative on the du I'm going to put out front. This is 1 minus u squared, and there's a u squared, and there's a du. And this integral is easy, because you can just multiply this to get u squared minus u to the 4th du, which is minus 1/3 u to the 3rd plus 1/5 u to the 5th plus c. Substituting back will get you minus 1/3 cosine to the 3rd of x plus 1/5 cosine to the 5th of x plus c. And maybe for you that's obvious that this is what the antiderivative of this would be, but giant piles of powers of cosines is not where I would have anticipated this to derive from. If you check this by using the product rule for differentiation, what you're going to get after you do a bunch of identities, a bunch of stuff cancels out and you can get this original function back again. But this is the general strategy anytime you have a problem that has an odd power of sine or cosine. So if you have an odd power of sine or cosine, reserve one and use identities to switch to the other function. So you can think of that as technique 1. Okay, so what happens if we have even powers of sine and cosine? Well, if you see only even powers of sine and cosine, you should groan, because those tend to be more work, because we have to replace one function, cosine squared, with two functions that are added together. So in the case of cosine squared, 1/2 plus cosine of 2x over 2. But that's the only way to integrate a cosine squared or a sine squared, is to use the half angle identities. So for integral 2, the first thing we're going to do is look at the most simple case that we can find, which is just what happens if we try to integrate the square of the cosine. So unlike secant squared, which integrates into a tangent, this does not have an easy, obvious antiderivative. And there's no way to do this except to use the half angle identity, which is cosine squared of x is equal to 1/2 plus 1/2 of the cosine of 2x. So I can replace the square with a single function at the cost of introducing a constant that I've added and putting a 2 inside with the x. This integral becomes then the integral of 1/2 plus 1/2 times the cosine of 2x dx. Those are both things I can integrate. I get 1/2 x, and I get 1/4 times the sine of 2x plus c. So this is the integral of the cosine squared, and there's really no other way to do it. If you get things that have even powers of sine and cosine, you have to use these half angle identities to reduce them. So how bad could this be? Well, pretty bad. Let's look at the integral of the cosine squared of x times the sine squared of x. Your first hope is that you can use u substitution here, but there's not an extra copy of cosine or sine that you can pop out to stick with the dx so that it can become a du. So all the powers are even. And so there is no way to proceed except with the half angle formulas. It's the only thing we can do. So using the half angle formulas, I get 1/2 plus 1/2 times the cosine of 2x, and 1/2 minus 1/2 times the cosine of 2x. Of course, I can't integrate this because it's a product of functions. So I've got to do something with it. So let's FOIL it out and see what we get. The integral of 1/4 plus 1/4 of a cosine of 2x minus 1/4 of a cosine of 2x. And then I'm going to get minus 1/4 of a cosine squared of 2x. So these cancel, that's nice. But look, we still have this extra squared cosine term left over. So what do I do when I see a cosine squared? I hit it with the half angle formula. So I have to do it again. In this case, I'm going to get the integral of 1/4 minus 1/4 times, okay, well, the cosine squared of 2x is going to be 1/2 plus 1/2 of, well, I took that 2x the last time, and I took x and multiplied by 2 to get 2x. Here I've got a 2x inside, so I'm going to cosine of 4x. And so this integral becomes the integral from, of 1/4 minus 1/8 minus 1/8 of a cosine of 4x. That was a lot of algebra, but finally I've arrived at a function I can integrate. I know the integral of the cosine of 4x. So this, so 1/4 minus 1/8 is 1/8, so you get 1/8 of an x. And the integral of the cosine of 4x is 1/4 of the sine of 4x. So you're going to get minus a 32nd of the sine of 4x plus c. So even powers of sines and cosines are nasty problems to deal with and algebraically heavy, but that's how the technique works when you have even powers. So that's case 2 for these trig products. Products of even powers of sine and cosine. Then the strategy is that you reduce using the half angle formulas. And you reduce and reduce and reduce and reduce until you end up with no power at all on the cosine that you end up with. So you can get lots and lots and lots of terms doing that. What about other trig functions? Well, we have the same kind of relationship between secant and tangent, except we have to reserve different sorts of things in order to do that. If we had u equal to the tangent of x, then du would have to be secant squared of x dx. So if I'm going to be working with secants, I need to have a whole secant squared living inside where I can peel out a secant squared out. If I have a substitution where I let u be equal to secant x, then the du would have to be secant of x times the tangent of x dx. So the method in each one of these cases is still u substitution, but they both apply to different sorts of integrals than they do in the sine and cosine case. With this information, here's the sort of integrals that we can solve. If we have a product of tangents and secants, and case 3, the power of secant is even, then we can steal a secant squared and convert all the secants that are left over into tangents. Reserve a secant squared x dx, convert to tan, and let u equal tangent of x. If, on the other hand, I know that the power of the tangent is odd, if the power of tangent x is odd, then what you can do is you can reserve a secant x tangent x dx and convert everything else to secants and let u be equal to the secant of x. So let's look at some examples of how that works. So as an example here, we have a problem where we've got an odd power of tangents. So tan x has an odd power. And that means we're in case 4 that we've been looking at. Case 4 says that I'm supposed to reserve a secant x tangent x. So we're going to have a tangent squared x and a secant x that are left over here. And then we've reserved ourselves a tan x secant x dx to be the du, because the substitution that we're going to want to make here is u is equal to the secant of x. So that du is going to be secant x tangent x dx. Now all this stuff I have left over, I'm going to have to convert all of this into nothing but secants in order for this substitution to make sense. And the fact that tangent was odd meant that when I pull out a tangent secant, I still have an even number of tangents here, which means I can apply the Pythagorean identity for the tangent function. So if you don't remember what the Pythagorean identity is for the tangent function, you can consult your handy dandy chart and see that tangent squared of x is equal to the secant squared of x minus 1. And yes, I did just look at that so that I would remember what it was. So I'm going to convert everything to secants by doing this. The integral of secant squared of x minus 1, that's where that tangent squared, that's what that tangent squared turned into, times the secant of x, times tangent of x, secant of x, dx. And now with the u substitution that I've made here, this entire thing turns into an integral of u squared minus 1 times u times du. And that's just a polynomial. So this is the integral of u to the third minus u du, which is 1/4 of u to the fourth minus 1/2 of u squared plus c. Substituting back in, we get 1/4 of secant to the fourth of u minus 1/2 secant squared u plus c. These are x's. If it's not the case that we have powers of sines and cosines multiplied together, or odd powers of tangents, or even powers of secants, then we're going to have trouble. The trouble that we're going to have is there's no technique in that case. Essentially, you're flying blind, and the method that you come up with has to be somewhat inventive, because you've got to choose a method based on the problem that you've got. In those cases, there's two more integrals that turn out to be useful. So it's useful to remember that the integral of the tangent of x is the natural log of the secant of x plus c, and it's useful to remember that the integral of the secant of x is equal to the natural log of the secant of x plus the tangent of x plus c. And with those basic facts, we can do some more integrals that are kind of in the same family but more difficult. So one example would be something where, say, we only have tangents. So that's a pile of tangents, but we have no secant squared that we can reserve to be part of a u substitution. So in this case, we're going to start with tangent cubed, and we're going to try to convert it into something that we can solve using some mixture of u substitution, possibly integration by parts, and possibly Pythagorean identities. The one I'm going to use here is I'm going to notice that I could rewrite this as the integral of the tangent of x times the tangent squared of x dx. And if I did that, I could take that tangent squared and I could use the Pythagorean identity to put it into terms of secants. The result is I can split this up into two integrals that I know how to do. I got a tangent of x times a secant squared of x. Well, that's just a regular old u substitution where u is equal to the tangent minus an integral of a tangent. But I know what the integral of the tangent is. It's right here. So if I want to finish this problem, this turns out to be 1/2 of the tangent squared of x using a very straightforward u substitution. So here, just let u equal the tangent of x. And then the integral of the tangent is the natural log of the secant. Okay. So Pythagorean identities are one way that we might approach a problem that is not a product of tangents and secants. Now, the most notorious of these, and one that when I was at Cal Poly turned out to be the problem that the professor threatened us with, like if we didn't behave in class, then he would give us this integral on our exam, is the integral of the secant cubed of x dx. And so I'm going to encourage you, without looking, try this one. And the key is going to be to use the correct integration by parts. So that's one that is one of my favorite exercises. I don't know if I would put it on an exam, but it's the kind of thing that if you put it on paper in front of you and you don't cheat by looking at how to do it, you can play around with all the techniques that you have available and see if you can stumble across the right answer. So if you're a math major or you're interested in mathematical proof, this is an opportunity to think like a mathematician. So there's your challenge. Find that antiderivative without looking at it. It's in the book, but I encourage you to do it on your own. So what did we learn today? In this section, we learned techniques for dealing with 4 different kinds of integrals. We learned how to deal with integrals that look like the sine of mx cosine to the n of x dx in the cases where m or n is odd. And when we did that, what we did was we reserved a sine or a cosine, and then we converted with cosine squared of x plus sine squared of x is equal to 1. So 2 of those cases were here. Then we learned where we've got sine to the mx, cosine to the nx dx, where m and n are even. And there the technique was to reduce using the half angle identities. So case 1, case 2. We also learned how to deal with integrals of the tangent to the mx secant nx, where m is odd. In that case, what we did was we reserved a secant x, tangent x, and converted to secant of x. And the fourth case was tangent mx secant nx dx, where n is even. And in that case, what we did was we reserved a secant squared of x and convert to tangent using the Pythagorean identities. So these are the 4 big techniques that we learned, and everything else was ad hoc. So work on these exercises. Identifying which of these things you're in, you can imagine, is more challenging when you don't have a guide like this in front of you, but you're going to have that in this class. So you shouldn't be intimidated by the integrals that you're looking at. So the way you're going to get facility with this is practice. So practice, 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 and I'll see you in the example video.